The next causal inference technique we'll cover is called regression discontinuity. This is the penultimate causal inference technique in our toolbox, so let's finish strong. In the world, there are many thresholds which yield binary outcomes. For example, if you are 21 or above in the United States, you can purchase alcohol legally. Otherwise, you cannot. When you are 16 or above in the United States, you can drive legally. Otherwise, you cannot. In most grading schemes in universities, scoring a 59 or below is a failing score, and anything above 59 is a passing score. The key insight of regression discontinuity design is this. Aren't the people right around the threshold more or less equivalent? For example, what really is the difference between a student who scores a 59.1 and a student who scores a 58.9? Sure, one gets a passing grade and the other doesn't get a passing grade, but besides that, can we realistically imagine these two people to be different? After all, their score differences are only 0.2. The regression discontinuity technique is based on this assumption that there's really no systematic difference between the people who are just below and above the cutoff. The best way to understand regression discontinuity is to go straight into a real-life example. In 1960, researchers Thistlethwaite and Campbell did a study to figure out whether scholarships had any effect on student achievement after school. In their study, the scholarship they focused on was the National Merit Scholarship, which required students to take a test. If they scored above a certain cutoff, they received a scholarship, and if they didn't, they received no scholarship. This graph is from their original paper from 1960. We have in the x-axis, the test scores. And on the y-axis, we have the percentage of students with given study or career plans. This is their proxy variable for student achievement. In the study, the researchers highlighted two types of outcomes. People pursuing 3 years or more of graduate school, and people planning to become a professor or scientific researcher. Their percentages are shown in the y-axis. Now let's look at the regression discontinuity idea. The basic idea is that the people who were just below the scholarship cutoff of 10.5 are essentially the same people as the people who were just above the cutoff, that is, their receiving scholarship was not because of any systematic difference. If we believe in this assumption, then any difference in the average outcomes between these two groups of people is solely attributed to the treatment of receiving a scholarship. Looking at Thistlethwaite and Campbell's graph, we can see that there is a jump into discontinuity in the regression line. It seems that people who get the scholarship do go on to pursue more education or a career in scientific research at a slightly higher rate. Now admittedly, the data is a bit noisy, which is why the researchers drew a regression line on both sides of the cutoff, to make it more distinct that there is a bump in student achievement due to the scholarship. But don't let the regression lines fool you. We are not comparing the haves and have-nots. We are comparing the almost haves and the almost have-nots. Why? Because it's only once we look close to the cutoff that students would be near equivalent in all observed and unobserved characteristics, such that confounding variables are no longer an issue, and treatment status becomes more or less randomly assigned. Okay, so how do we actually run the regression discontinuity design? Broadly speaking, there's 3 common ways. The first method is called nearest neighbors. Here, we are going to draw a small bandwidth to the left and right of the cutoff, and take the nearest neighbor of points that fall within. Then we take a simple average of these two groups and compare the averages. This is our treatment effect. How large our bandwidth should be depends on the context. And it's a trade-off that you have to figure out. The smaller the bandwidth, the more likely it is that the treatment assignment becomes random, but we won't be picking up much data points. And statistics will tell us that the more data points we have, the more we can be confident about a sample statistic. But at the same time, the more we increase the bandwidth, the higher the chance that we are picking up the confounding effects of higher test scores. So the tough question you have to answer is, how close is close? How do we balance getting more data versus looking close to the cutoff? The second method is using what's called a distance kernel. And the idea of the distance kernel is that we want to look at many more points than we can, with a narrow bandwidth from the nearest neighbors method, but because in doing so we sacrifice locality and expose ourselves to confounding variables, we want to weight points which are far from the cutoff, much lower than points which are close to the cutoff. So you can think of this method as trying to get the best of both worlds. With distance kernels, we can factor in more points than we can with just a small narrow window near the cutoff, but also try to prevent the influence of confounders by putting much more weight on the points near the cutoff. This graphic shows the most commonly used kernels. The y-axis you can think of as the weights, and the x-axis you can think of as distance from the cutoff. Note that each kernel has a different way of assigning weights. Some taper off really quickly, whereas others are really smooth. The third method is what Thistlethwaite and Campbell did in their research. Basically, we do a regression on the left-hand and right-hand side of the cutoff. Then calculate the difference between the two fitted points at the cutoff. This is our treatment effect. At this time, I want to point out that what we have described thus far is called a sharp regression discontinuity design. Basically, it's an all-or-nothing situation. You either receive the treatment if you are above the cutoff, or don't receive the treatment if you are below the cutoff. One other thing you should note is that there is also something called a fuzzy regression discontinuity, and this occurs when rules are not strictly enforced. For example, perhaps the scholarship from our previous example is not solely determined by SAT scores, but students above the cutoff get a higher chance of receiving the scholarship than those below it. Therefore, the threshold here is fuzzy. It concerns a discontinuity of the probability of receiving treatment. This means that students above the threshold may not receive the scholarship, and those below the threshold may receive the scholarship. Fuzzy regression discontinuity problems can therefore be solved using instrumental variables analysis. If this is hard to imagine, convince yourself of this by revisiting the module on instrumental variables and going through the 3 assumptions which need to be met for an instrumental variables analysis. Fuzzy regression discontinuity is one form of instrumental variables analysis. We are going to revisit Sandra Black's paper, Do Better Schools Matter? Parental Valuation of Elementary Education. If you can recall, we covered this paper in the regression module. We noted then that Black's first approach at the problem used a controlled regression to find out the effect of school quality on home values, and found that the magnitude of the test scores coefficient, which was a proxy for school quality, indicated that a 5% increase in the average elementary school test score was associated with a 4.9% increase in the home value, an increase equivalent to almost $9,200 at the mean home value. But Black also thought that the controlled regression did not suffice, because she couldn't control for all relevant house and neighborhood characteristics, which biased her estimate of the impact of school quality on home values. Black uses the regression discontinuity approach to remove the effects of confounders. In the United States, children go to the school based on the location of their home. There are attendance zones which demarcate the homes which are designated for a particular school. And basically, the idea of Black's study was to compare houses on opposite sides of a common primary schooling attendance district boundary. The assumption she makes is that changes in school quality are discrete at boundaries, while changes in neighborhood characteristics are smooth, meaning that unobservable neighborhood characteristics correlated with test scores are the same on each side of the border. Therefore, comparing home values of two families who live in opposite sides of the same street, but are zoned to go to different schools, would be a good estimation of people's willingness to pay for school quality. Black describes this as the marginal willingness to pay for a better school. And this is in her words, why regression discontinuity would be useful for this problem. If this assumption is correct, then difference in mean home values located on opposite sides of attendance district boundaries can be attributed to the differences in primary school exam scores only. Researchers will try to confirm their assumptions if they can. This is Table 3 from Black's paper, which shows that houses on opposite sides of the boundary do become similar, when the sample is reduced to houses that are close to the boundary. What Black uses to calculate the causal effect of the average test score on the home value is a regression of this structure. And it's important to note here that this regression is not the same as a controlled regression we discussed in an earlier module, and Black makes this clear by stating that her methodology is equivalent to calculating differences in mean house prices on opposite sides of attendance district boundaries. The treatment variable here is the average test score of the school associated with the district the house is placed. Therefore, the coefficient represented by the Greek letter gamma, is the focus of the study. Black also keeps her original controls from what she called the hedonic regression model, more or less the controlled regression model that she used as her first attempt at cracking the problem. These controls are number of bedrooms, bathrooms, and neighborhood and school district characteristics that will help us move towards ceteris paribus even more. These are the results, and the key thing to note is this. The coefficient, gamma, of elementary school test score in column 5, the number 0.031, was the result Black got from the basic hedonic regression, remember just the controlled regression. But the coefficient for the regression discontinuity model, which she labels as, with boundary fixed effects, the number is 0.015, roughly half. The interpretation? The naive estimation using the controlled regression was a pretty biased estimate. If we do not carefully control for neighborhood characteristics, we would be greatly overestimating the value of additional school quality as measured by test scores. The conclusion? Black writes that parents do care about school quality as proxied by the elementary test scores. The measured effect. Parents are willing to pay about 2.1%, or $3,948 more for houses that are 5% higher at the mean. While regression discontinuity is very intuitive and often really nice, there are a couple potential issues that we have to be wary of. The first is one we've covered. That the sample size is usually not very big at the threshold, and it's really ambiguous how we go about choosing a good bandwidth. We want to reduce unobserved differences between the two groups, but at what cost? The second problem is that there may be other rule changes happening at, or near the same threshold. Referring to Thistlethwaite and Campbell's study, if students who get a score above the threshold, and get a scholarship, and on top of that, receive other benefits, like the chance to study abroad, or apply to fellowships, the effect we would estimate would be the combined causal effect of getting the scholarship, the chance to study abroad, and apply to fellowships, and not simply the causal effect of receiving the scholarship alone. The third problem is that regression discontinuity designs can be invalidated if people manipulate the treatment assignment. As long as subjects can't manipulate which side of the threshold they end up on, we can treat the assignment as random. However, if students know that they can receive a benefit if they reach above a certain threshold, they can effectively choose their way into the treatment. One way to test for this is by checking whether the people just below the cutoff are similar to the people just above the cutoff. If there are more people on one side than the other, individuals may be controlling their assignment. The fourth is the concept of external validity. In regression discontinuity, we're estimating what is called a local average treatment effect. The effect pertains to people in a narrow, or local range around the cutoff. If there are different treatment effects for different types of users, also called heterogeneous treatment effects, then the estimates may not be broadly applicable to the full group. If you want to learn more about other studies which use regression discontinuity, these are the resources I recommend.